Okay, hello everybody. We can start. We are waiting for the last people that is connecting with us, but now I think that with 5 minutes late, we can start our webinar. Thank you to everybody to participate to this webinar. We are very proud for your presence because today we are near to 100 people connected to us. I'm Guido Noce. I think that most of you know me, probably not everybody. And we are in Dimac. We are in our showroom. I will show quickly after. Now I have the role to introduce this meeting, but before doing this, while we wait for the last people that will connect, I will introduce Dimac. Shortly, Dimac. I think that everybody of you know us for our 100% sorting machines. We work also for in the world of the SPC and the shop floor, and all of this vision is we call this vision zero defect factory. Zero defect factory for us means that all the infos about quality could be integrated in only a vision, only a system, and this can give synergies that could be very interesting for our customers. As you know, we are specialized in metal components. The quantity of different shapes it seems incredible. We count about 500,000 of different shapes and parts that are selected by our machines in the time, and about 20 billions of parts every year. Okay, today we want to show something to you about artificial intelligence. I come back to my camera on PC, but my short introduction is near to the end. I want to show you our set for today. And as you can see, we have more than one camera, and here we have the direction of our film, of our movie, and you can see that a lot of tools and machines are ready for you, and Gabriele is waiting for starting to the demo. You can make answer to us using the chat. We have also connected with us Simone Silvestri, that is our sales manager. And so, Alan, you can start with the show.
Great. Thank you. Hello, everyone. As Guido mentioned, I'm Alan Okana, and I'd like to begin by joining him and thanking all of you for joining us today. We're especially proud to welcome attendees from all corners of the world. Your presence reflects global interest in these technologies, and it's really a privilege to share Dimac's work with such a diverse and involved audience. All right. With that said, we'll go ahead and begin the presentation. Click here. Okay, so let's begin by framing the core topic of today's session, crack detection and fasteners, and the technologies used to ensure safety and reliability across a wide range of applications. As you can see from the slide, not that slide. Let's go back. As you can see from the slide, crack detection is essential, but not just for quality control, but for maintaining long-term performance and critical components. Today, we'll be focusing on two of the most widely used inspection technologies in our sector, eddy current systems, which many of you already be familiar with, and AI-based optical inspection, which is now emerging as a powerful complement. Um, and throughout the presentation, we'll walk you through several case studies. We'll also show you how these technologies work in practice, both through slides and short videos. To begin, I'd like to share a brief video we produced a few months back, which introduces the topic and sets the stage for today's discussion. So Guido, if you can please share the video.
AI for AI, artificial intelligence for automatic inspection. Fastener manufacturers rely on Dimac sorting machines to carry out 100% quality control and to automatically reject defective parts before they reach the market. Millions of screws, bolts, and metal components are fed into the sorting machine, where each part is individually inspected using high-resolution cameras or mechanical devices. A dedicated software system processes the data in real time to verify part compliance. The inspections cover dimensional checks and defect detection, including cracks, burrs, scratches, thread damage, and stamping defects. This process is extremely fast and highly accurate. Once the inspection is complete, the machine separates the good pieces from the waste. Until recently, certain defects could only be identified by the trained eye of an experienced operator. But with the introduction of artificial intelligence, human visual inspection can now be replicated and enhanced by advanced AI technologies. Dimac was the first company to apply AI-driven vision systems to quality control in the metal fastener industry. The AI tools developed by Dimac compare real-time images captured at inspection stations with a synthetic image database generated through AI, instantly detecting any non-compliant parts. Controls become even more efficient. The range of detectable defects increase, and the margin of error in the sorting process is reduced. In the application, Dimac successfully addressed several technical challenges, integrating traditional computer vision methods with AI-based analysis, overcoming the lack of real defective parts for training, by developing systems capable of learning from similar but distinct scenarios, ensuring flexibility to enable future-ready, service-oriented systems. This makes AI for AI a scalable and adaptable solution, ideal for any inspection process that requires the discernment of a human visual check, while delivering significantly higher speed and a much more accessible training workflow. Artificial intelligence for automatic inspection for a zero-defect future.
Now, what you see on this slide is a selection of sample parts, actual components from production lines, which we'll examine in more detail shortly. We'll go through them one by one, and Gabriele will join us later to help illustrate how each case was handled from an inspection standpoint. All right, let's take a closer look at how eddy current crack detection works in practice. Until about 2 years ago, eddy current was the only effective method for crack detection. On our machines, we routinely use eddy current systems, such as Marpos or IBG. Most of you are likely already familiar with it, but I'll briefly recap the technology. Um, what we have here is a dedicated inspection unit. You can see it in the photo, equipped with one probe or sometimes two, depending on the configuration. The inspection process involves rotating the part in front of the probe. As it spins, the probe generates an electromagnetic field, which induces eddy currents in the material. Any discontinuity, such as cracks, disrupts the flow of these currents. Um, that disturbance, let's call it, is picked up by a receiver. And by analyzing the signal during rotation, we're able to detect material anomalies, most of which are attributed to cracks. Now, this technique is highly sensitive, so structural irregularities, and it's particularly effective for identifying internal or surface level defects that aren't visible to the naked eye. So to illustrate this, we'll show you a short video of the machine in operation. And Guido, if you can please start the video for us. As you'll see, the parts will start entering the machine below and then pass through the eddy current inspection system. The red histograms you see on the screen represent non-compliant parts. Those flange as defective by the IBG system. Here's a slow motion view. The parts are lifted and rotated in front of the probe, which is a critical moment in the inspection cycle. Now, this phase is extremely delicate. Even the distance between the probe and the part must be carefully controlled to ensure reliable detection. And again, you'll notice the red histograms. These are the system's way of identifying parts with crack-related anomalies. Um, so that, in essence, is how the machine operates. Go back here. Yes. It's a compact, high-speed solution for non-destructive testing, and it's widely used across Dimac platforms for crack detection and material integrity control. Let's now take a moment to review the key operating characteristics of eddy current inspection. First, the system relies on a probe that detects material discontinuities within approximately 3 millimeters from the tip. This sensitivity allows us to identify subsurface cracks, often referred to as underskin defects, which are not visible to the naked eye. Second, for technology to function correctly, the material must be magnetic. Third, but that's not enough. It also needs to be homogeneous. Surface damage, such as dents or lateral marks, can interfere with the signal and may be misinterpreted as cracks. And fourth, as mentioned earlier, that the parts must be rotated in front of the probe. And to ensure a reliable reading, it needs to complete at least 3 full revolutions. This requirement, sorry. Can you guys hear me? Yes, great. So at least 3 full revolutions, right? The requirement naturally limits the inspection rate to around 120 to 125 parts per minute, especially when high precision is needed for components in the M6 to M10 range. Fifth, another important constraint. Inspection is typically performed on one or most external circumferences of the part, usually outer excursion rings or flange surfaces. What does this mean? This basically means we're not able to detect internal cracks or defects located deeper within the part's geometry. We'll look at a few specific examples of this later on. And six, the part must have cylindrical geometry, hexagonal, octagonal, or irregular shapes like nuts or custom profiles. Can't be reliably inspected using this method because the probe requires a consistent distance from the surface throughout the rotation. Now, let's take a closer look at some of the critical limitations of eddy current inspection systems. As mentioned earlier, the probe must operate at a very precise distance from the part surface. This is essential for signal accuracy, but in practice, it introduces several challenges. If the part has wide production tolerances or slight deformations, some areas may rotate closer to the probe while others drift further away. This, let's call it inconsistency can lead to false rejects, especially when the surface has minor dents or acceptable irregularities. The system may interpret these as cracks simply because they fall within the probe's, let's call it, sensitive zone. On the other hand, if a real crack happens to be located in a spot where the part is slightly further from the probe, there's a risk that it may go undetected. Another issue um, to consider is mechanical interference. In some cases, specifically with larger or less uniform parts, sections of the component may come too close to the probe, causing physical contact. This can result in probe damage, which is not disruptive. Well, it's not only disruptive, but also costly, typically in the range of 2,000 to 3,000 euro per incident. Now, these limitations are important to keep in mind when evaluating whether eddy current technology is suitable for a given application. And they're summarized here on the slide, meaning risk of false rejection is part of surface is not perfectly smooth, and risk of probe damage in the event of open cracks or residual material on the flange. And we'll explore a few specific examples of these cases in the next section. The limitations we just discussed have led to many of our customers to ask for alternative solutions, especially for those blind spots that traditional eddy current systems struggle to cover. Until late 2023, there were few viable options, but thanks to recent advancements in artificial intelligence, we've now developed a series of optical inspection systems that can either complement or, in some cases, support applications where eddy current is not feasible. So let's talk about this new approach. In principle, the idea is simple. AI simulates the behavior of the human eye. Once it learns what a defect looks like, it applies the same inspection logic to all subsequent parts. This brings us to a key distinction. AI systems require the defect to be visually detectable. That means we can reliably identify surface level cracks, scratches, and visible anomalies. But subsurface defects such as underskin cracks or internal material inconsistencies are not visible and therefore not detectable using this method. Now, to operate effectively, especially at high speeds, high demanding speeds, AI software also requires dedicated computing resources. We're talking about high performance GPUs or graphic processing units, which are optimized for parallel processing and essential for real time image analysis. And it's not only thanks to recent availability of affordable high speed graphic cards that this technology has become scalable and accessible for industrial use. That said, it's of the utmost importance to note that eddy current remains a trusted and widely deployed solution, particularly for detecting subsurface cracks and material discontinuities. What AI does, on the other hand, is offer a new layer of capability focused on surface level anomalies, which can enhance traditional inspection setups and fill the gaps where optical methods are more effective. All right. Now, let's take a closer look at key feature and development milestones of our AI based inspection systems. First, as we've seen, these systems are designed to detect surface level cracks, those that are visible to the human eye. And this is a natural fit for optical inspection. And it allows us to train AI with high precision. Second, to meet the demands of high speed production, we've invested in efficient training workflows and high performance computing platforms. Our systems rely on dedicated PCs with advanced GPUs, enabling real time image analysis without compromising throughput. Third, uh, we've also prioritized inspection reliability. And to maintain consistent quality, the system is calibrated to exclude any case that appears ambiguous, ensuring that only fully compliant parts are accepted. And finally, once the more interesting challenges we've solved is the initial lack of defective samples. In early production runs, parts are often flawless, which becomes or which makes AI training more complex. But thanks to our internal data set and collaborative efforts with our customers, we've built strong models that continue to improve over time. Uh, at Dimac, we've been working on these technologies since 2023. And today, we have AI applications that have been in use for nearly 2 years, particularly in the fastener inspection sector. Um, and the feedback from our customers has been overwhelmingly positive, and it confirms that we're definitely moving in the right direction. So, with that said, ladies and gentlemen, thank you all for your attention. I'll hand things over to Gabriele, who will guide you through the next section and show you something a bit more visually dynamic. Thanks again and enjoy the rest of the presentation. Gabriele, please take it away.
Thank you, Alan, and thank you to everybody for joining our webinar. I'm Gabriele. Maybe someone of you already know me. Now, before starting with our with my presentation and with my demonstration, I just want to give you a look what is our set and what is the equipment that today we have ready for demonstration. Okay, here we can see a white room with some parts that I will show you later with some defect, and the one station, one bench with one top camera with the AI and with the motor controls of the arms. Okay. On the right, you see another bench with the with the 4 camera that 90 degrees positioned in 90 degrees. And you have and you can see also the lights and the monitor behind. Here you will see the bench with the linear camera, with the linear scanning camera. Probably someone of you already see in other webinar. And in the end, the last thing that you can see is the machine. This is a one MCV6. Inside the machine there is the same 4 camera that you can see on the bench. There is also inside the machine, just to see the practical application on the machine. And okay, so this is our set. Now we can start to see some parts that help me to show you something today. Okay, we can go on the white box. Okay, so this is the first part that you that you can see there is one crack. This is a classic stainless steel screw, normal screw, but the one of the issue that we found with this screw with the eddy current is the material. With this kind of material, not always the response of eddy current can be reliable to see this kind of crack. With the AI, we don't have this kind of issue because we see the crack by a vision system. Okay, so the second part that I want to show you is a little bit bigger. Is this part. Also, this one you can see that have a crack on the head. Okay, the material is mostly the same of the other screw. Okay. The third part that I want to show you is in an hydraulic nut. These parts, as you see, have a big crack, but the problem is that this is not circular. So with a normal probe, eddy current probe, we cannot check a part like this because the surface is not regular. And so also if we have a big crack, this one cannot be visible with a normal, with the eddy current. Okay. And the last part, not the last, but the other part that I want to show you is this one is like a column, okay, that have a big crack on the head. Also, this head, as you see, you have two circumference, one internal and one external. If the crack is big like this, probably you can see easily also with the eddy current. But sometimes can happen that some crack like this can be only in the internal circumference, in the internal parts. In this case, with the eddy current, you cannot see this kind of defect. And in the end, I show you one big part. This is one shaft. Okay. In this case, the area of the crack it's very big. Okay, it's very big, the area. So it is necessary to put two probes because with only one probe it's difficult that you can check all the crack, because one of the problem that you can have in this part is that in this case the crack is all around, is all along on the flank, but in some other case, for example like this, you have the crack only on the bottom of the part. So if you don't have two probes, it's difficult to find this crack. And working with two probes sometimes can be some more adjustment on the machine. Another things that you can have in this kind of parts, that sometimes these parts can have a shock on the flank, on the surface, and some of this shock can be confused for the eddy current as a crack also, and it can create false reject. So this is more or less the parts that we want to show now. The first station, the first bench that we want to show you is the 4-camera bench. Okay, here we can have the bench. Okay, now I take the first part. As you see here, we have an illuminator and also a top illuminator and the 4 camera. And now we go to put the first part on the bench. Okay, As you can see on the image here, we can see the 4 cameras that take a picture on the parts, and one of these catch the cracks. In this case, the catch is marked with a blue blob that identify where is the crack, and you see that it's possible to easily detect the crack. Now, always with the same parts, I just want to show you another part with a defect like this. Okay, what you can see here is that in this case, the parts have 2 different defects. One defect is the cracks that we see below in the other parts, but in this case, we have also damage, a shock on the thread. This can introduce another topics, so that it is possible with the AI system to implement more than one feature. In this case, we have 2 features in this training. That's the name is cracks and thread. We have 2 features. These parts can be detected both cracks and also a defect on the thread, for example. Okay, now I show you the next part. Okay, this is the other part that I showed before, and also in this case you can see that the machine detects the cracks. In this case, detects also something else because the part have a different dimension. So it's possible that need to adjust a little bit some value to filter all this kind of disturb, but the cracks is perfectly detected also in this case. Now I can show you the nut. Okay. Here you can see this is a very big damage. So you see in more than one image. Here you can see easily the big crack. But one very interesting thing is that, for example, in this image, you can control also the internal part of the thread. Here you can see also a damage on the internal, because in this case you have a very big crack, and it is possible to see also an internal damage, for example, in the nut. And this is obviously not possible with other kind of system. Okay, now we can pass to the other bench on the top camera bench. This one. As you see in this bench, we have another new things that's probably mostly of you, also people that know our machine, never see, is the 2 motor on the station. These 2 motor control the 2 arms that have this machine. So the camera and the illuminator. The reason for this is because the artificial intelligence software for work need to restore perfectly the image as at the same light and condition that we found during the image acquisition and training. Sometimes this can be tricky, okay, because especially if you have more than one arms, more than one machine, can be difficult to find exactly the same position of the illuminator. So in this case, in this station, we have 2 motor and an HMI software. This the HMI software that can allow us to put and save a receipt with with a specific position of the arm, and put the arm automatically in the correct position. So now I will show you how the station move. Okay. Okay. As you see, the station automatically move and reach the correct position. Okay. Now I just put the parts with the cracks that I showed before. Okay. And now you can see that also in this case, it is possible to see easily a big crack that you have on the parts that is identified with a red rectangle that can put in evidence what is the crack. Now I show you just another part like this, but with a small crack. Okay, so this is another part that you see that have a very small crack only in the internal parts of the in the internal circumference of the parts. In this case, it's very difficult to see, probably impossible with an eddy current, because the eddy current work only in the external area of the parts of the piece, and then it's very difficult to catch a crack like this in without with the other kind of system. And in the end, just to put the conclusion of my presentation, here we have light scan. Light scan, for the people that do not know this kind of technology, is a particular scan that make a vertical scanning on the parts and then put a development on the parts. So it's like if you have your parts, a cylindrical parts like this, the concept is that you cut the parts and you develop in 2D, in 2-dimension parts. And so you can have all the strip of your parts. And then in this case is also possible with the specific light that we have very strong light that is, for example, in this case, it is possible to identify sign, damage, and also crack. For example, now you can see, for example, in the skin, you see, for example, a vertical crack on the parts, and this is another possibility. Possibility to see this kind of defect. Also, this one can work with an AI, an artificial intelligence software that detect this kind of part, and it's also possible to filter all not crack, but is only sign on the parts. Okay, so more or less I finish my presentation, and now I give back the words to Alan, then say to you something about the training on the AI equipment. Thank you very much.
All right, thank you, Gabri. So we want to briefly walk you through the AI training process, a service we provide directly to our customers. Let's begin with step one of the training process, image acquisition. This takes place directly on the sorting machine in production using a tool integrated into the machine interface. Operators capture real images of the components, including both conforming and defective parts, under various operating conditions, such as different lighting, orientation, and surface states. This step typically takes around 30 minutes, and it provides the raw visual data needed to train the AI model. Once the images are captured, the process moves to Dimac's AI specialist, who handle the next step or the next phases remotely. Step two, Dimac connects the machine remotely and downloads the image set. Alternatively, the customer can send files via a secure transfer service. Step three, we perform defect annotation, either manually or using semi-automatic labeling tools. If needed, we apply data augmentation, creating a new image variations through rotation, zoom, lighting changes, and more. When real defect samples are limited, we also generate synthetic images using photorealistic simulation and procedural modeling. This includes simulated defects like scratches, cracks, dents, and surface contamination with controlled random variations to improve model strength. Step four, Dmac's AI specialists handle the training and validation remotely. Part of the data set is used to train the neural network, while the rest is reserved for fine tuning and reliability testing. This phase typically takes 3 to 5 working days. And finally, we've reached step five, deploying trained model. Once validated, the neural network files is uploaded to the user sorting machine, either via remote connection or email. The operator then links the trained neural network to the control recipe, which takes approximately 2 minutes. From that point forward, the model is automatically called whenever the recipe is loaded, ensuring samples integration into the inspection workflow. This completes the AI training as a service cycle, a fast, scalable solution that brings advanced vision inspection directly to your production line. All right, everyone. So we'll move into the Q&A portion. Please feel free to send your questions if you have not already done so through the chat, and we'll address them in the order they are received.
So please don't be shy. We wait for your question.
I don't know if we should take this as a good or a bad sign. Maybe we covered everything, but please don't be shy to ask any questions.
I start with a question for Gabriele, and one of the questions that often we have
Okay,
is...
are coming.
they're coming. Okay.
So can we use this for detecting crack inside forged parts?
Who can give an answer? Gabriele. Gabriele, you can speak.
Yeah. Okay, so mostly yes, so can be possible. Can be possible. It depends if it's possible to see inside of the parts. Obviously, this kind of part and the bench that you see on the demonstration is also useful for us for understand if it's possible or not to see something. But theoretically, if a defect is visible by eyes, and so is in a part that is visible by camera, can be possible to detect. Maybe need to see and to understand a little bit more this kind of forging parts, but probably yes. Yeah.
They ask us if we have some example of where the defect is inside, like a nut. But we show one of these.
Yeah.
Obviously, in this situation, we have also crack outside the nut, but we have also other examples. We have worked on other examples, but we don't have nothing prepared now, isn't it?
Yeah,
Gabriele?
not now. Yeah, yes, correct. This nut that you see before in the demonstration is an hydraulic nut that have a big crack, and it is possible to see inside because the crack is also inside. Obviously, we're talking about a glass dial machine where it's possible to put the nut in a position, and we have to orientate the nut just to have the visible area with the crack by seeing with the camera. But the interesting things with the 4 cameras is that you can inspect the 360 area of the surface without stopping the part. For example, in a glass dial machine where there is not a possibility to stop and rotate the parts, but you have to take a picture during the parts movement with the 4 camera like that I showed before. It is possible to see internal damage also on the nut or washer or other kind of parts like this.
Another question, Gabriele, I think that you can answer also to this. Can the machine detect turned heads as well?
Yeah, so sorry, what is the
Turned heads.
Turned heads?
Yeah. So of course, if the parts it's possible to run on the machine, we can check it. So this is it is absolutely possible also to check turned head maybe.
Yes, I add that we are seeing application on a glass table machine, but obviously we can use the same technique on other machines for hangable parts or also for robotic machines and movements, slow movements or hand movements machines for SPC controls. Next. What is the specific algorithm that we have used? Specifically, what kind of ANN algorithm and what is the method called? It is kind of an image classification. Okay, we don't want to give you too much information about technical details, but yes, it is an image classification. We use more than one software. We use commercial libraries. And more than one commercial libraries at the moment. So we are creating an experience wide in the market. Can you detect missing crimp while sorting for cracks as well? Gabriele, can we detect missing crimp while sorting for cracks as well?
It's a second feature.
Yeah, with the second feature, as you see, for example, in the case that we have crack and damage on the thread, if it's also possible to add another feature. Obviously, more feature you have on the training and more heavy is the training, and also a little bit longer is the response of the training. Traduced on the machine speed, the machine speed can be reduced a little bit more, but this is another kind of topics. Okay, but yes, it is possible to put more than one feature in the same training, of course.
One of our interesting development that is near to be released is that we can also measure take measure on the same image that we use for artificial intelligence. We have seen diagonal cameras, and so in these images it's strange to take measure, but when we work on from a top camera, it's possible to take also measure of the flange or other. We can surely do more than one neural network working on the same image. Obviously, the problem could be the time to work to do the evaluation, and so the machine could be slow. But with standard the standard timing for the inspection for artificial intelligence with normal application, one defect could be something that permit to the machine to arrive to 700 parts per minute. So when we speak of 30 parts per minute, 50 parts per minute in general, we don't have any problem with complex neural network training. Can you detect, no, sorry, if possible, detect discontinuities on the flank, on the thread that are very visible by means microscope with eddy current or AI?
So the main point is that, as Alan said before, is that the crack must be visible by eyes. Okay, this is what mean about artificial intelligence, because to teach to the system to recognize a defect, crack, damage on the thread, on the other kind of defect, must be visible by the camera and by the eyes, obviously, otherwise it's not possible to see it. With the eddy current, it is more possible to see. The critical things on the eddy current is the position of this crack, because I have to reach the part with a probe during the rotation, the 360 rotation of the part. So normally with the eddy current, it's also possible to see very small crack or crack under the surface of the parts. The criticity is first the speed, but also the necessary to arrive very close to the parts with the probe.
Another question we have from our attendees: could we implement this technology on mass production level, just like for automation, in which part coming from one side and we are checking it on mass scale in assembly line?
I think that this question is not so easy to give an answer now. I think that we have to check case by case to see if there is the possibility to implement the technology in already existing line or other thing like this. I think that this be correct, Simone. What do you think?
Yes, definitely yes.
Okay.
Yeah.
Another question. Oh, sorry. Go ahead, Simo.
No, so you can ask us and send an email, and we can evaluate together.
Okay, we'll probably have time for one more question. We're approaching 5. Can we use the 4-camera system where multiple parts are laying on the glass?
Yeah, no. On the glass,
we analyze one part
at a time.
Yeah, we need to analyze one part by one. So it is not possible to see multiple parts, but we need to have the parts that pass one by one on the behind the cameras.
But perhaps the question is if we can have 4 different images of the same part with different defects. This happens, and we work on this. Okay. We jump one question that is: what is the difference in inspection speed between eddy current and artificial intelligence?
Oh, wow.
Okay, so the speed can be can be a big difference. So because if you think that with the eddy current you have the necessity to stop the parts, rotate the parts, and you need more or less at least 3 complete revolution of the parts in front of the probe. And so normally with our machine, we talking about hangable parts. We can arrive around 120, 125 parts per minute. With the AI, with the same control, with the AI, we can reach considerable speed, also up to 500-600 parts per minute.
In general, it depends from the kind of acquisition, or the image acquisition that we use. If we use a linear camera like the one that Gabriele showed before, obviously the time is the time for turning the part in front of the linear camera. So in some situation, the speed could be comparable. In other situation, artificial intelligence could be really faster. So in general, with the current, we arrive no more than 200 parts per minute. With artificial intelligence, it could be from 100 to 600-700 parts per minute, depending from the acquiring cameras. Will your team send out the recorded version of this webinar to the participants? Yes, sure, you will receive. Can we detect crack on the surface layer, which is not visible means layer which exists between outer and inner layer? Don't understand the question.
Can we detect crack on the surface layer, which is not visible, means layer which exists between outer and inner layer?
I don't understand
but
the question.
Are you meaning like on a bearing surface, like on a bolt on a bearing surface? Yes, got it. So again, if it's an area that we can offer to the camera, okay, yes. Okay, for example, on a bolt that can lays on a glass, so we can lay upside down on a glass. So in order to have a full view of the bearing surface, yes. Otherwise, if it's not possible, in that case, eddy current is still the best option.
Okay, Okay, we don't have any more questions, so we can thank you everybody for your presence here. As we said, the version of this webinar will be distributed in the next days. We will send you also a quick questionnaire about the webinar to help us to organize a new appointments that are interesting for you. Thank you very much, and hope to see you the next opportunity.
Bye.